All right, thank you very much. It's great to be here with such a big crowd, and after that virtuoso performance by Jan and Ali. What I'd like to do in the minutes that I have is give you some context of where Spark came from and a little bit about how we do work in the AMPLab, and then tell you where we're going and give you a heads up for some things you might want to keep your eyes on. So the AMPLab is a research project at UC Berkeley in the computer science department. And our focus has always been on collaboration. So it's a pretty large project as far as these things go. It's about 60 people. This group of faculty that represent a bunch of different areas, computer systems, networking, databases, machine learning, security, and so on. We've got tremendous support from industry. I know many of the people here are people who work with our sponsors. We got support from the White House that announced a large big data research initiative that we were one of the main projects that were in that original announcement. And you know, the support has been really instrumental to us being able to think big and really do big things. And in addition, I'll tell you a little bit, and you'll hear a little more later in this session, about not just the applications we build, but we also, drive our work through real-world applications. And we've got some big efforts in genomics, in mobile sensing, and in some collaborative energy-saving projects. Okay, so sort of at a big brush, that's what the AMPLab looks like. Where the name AMP comes from is from the three resources that we believe you need to integrate to make sense of big data. So A stands for algorithms, so think about machine learning and statistical methods and such. M, machines, cluster computing, cloud computing, being able to scale up to deal with bigger and bigger problems. And the P is people, and we look at people in two ways in our project. The first being thinking about individual analysts and groups of data scientists. The second, which is a little more interesting maybe from or novel from a research point of view, is to think about crowdsourcing and human computation. So how do we use large numbers of connected people to help find data, to help clean data, to help do analytics? Okay, so AMPLab is the integration of those three resources, algorithms, machines, and people. And if you think about it, there are tremendous technical challenges here because all three of these resources, in addition to being very different and difficult to integrate, they've all got a huge amount of elasticity and dynamism. So, if you think about machines, obviously cloud computing brings, elasticity, multi-tenancy, increasingly deep storage hierarchies and so on. So lots of degrees of freedom there. But if you look at the other two dimensions, algorithms, many of you know about our work on BlinkDB and related projects where you get to trade the amount of processing you do for the answer quality that you get. If you look at machine learning, there's huge numbers of algorithms and libraries and things that you need to combine. So there's a lot of elasticity there. And of course, things like active learning, where you're changing the processing on the fly based on what you're seeing in the data, brings even more elasticity. And then of course, people are highly dynamic. If you think about task marketplaces like Amazon Mechanical Turk and other things, huge ability to bring resources to bear on a problem when you need them, similarly to the way you bring computational resources into a cloud. So we've got three very different resources, and all of these resources are very complex and continually changing. And that's really the research problem that we set out to address. So we created this thing called the Berkeley Data Analytics Stack. The acronym is BDAS. Many of you know that it's pronounced badass. And here's a few of the bets we made when we designed badass. One is, we were very cognizant of where commodity hardware was going in terms of in-memory processing. Spark obviously demonstrates that, and scalable storage and such. Our focus all along has been on advanced analytics, so not just running SQL queries, right? Not just generating reports, but doing real machine learning, dealing with graphs, dealing with all the different ways that you might want to deal with big data. The ability to trade off how much work you do, how much time you spend, and the answer quality you get. Because when you're doing analytics, sometimes you don't need a perfect answer. And that gives you flexibility to get faster answers, to get cheaper answers, to get bigger answers. So also things like relaxed consistency. Integration across not just the algorithms, machines, and people, but also different ways of doing analytics. So batch analytics, interactive analytics, streaming analytics, and so on. And then finally, as this meeting here is a testament to, from the very beginning we were focused on open source. And so we put a lot of effort into building community. We ran, as Andy mentioned, AMP camps to train people on what we're building, bring in people from outside the lab to help collaborate, to help us build the systems. And this has been a tremendous multiplier for what we've been able to do. All right, so this is what the BDAS project has been leveraging. So you're all here because you know about Spark, but what's happened since we started the lab in 2011 is we've been building software, and eventually that software graduates. So one of the first things to graduate was Mesos, and now that's an Apache project that's doing cluster virtualization. As you're all aware, Spark recently graduated. It moved to Apache as well. And as these projects graduate and move out of the lab and take on a life of their own, we don't just sit there on our laurels or whatever. We keep going. So we've been building a bunch of stuff. We've got some of the best graduate students and researchers in the world, and they're not sitting around. They're building the next generation of big data analytics. And so this is the current snapshot of our system. It's going to change over time, and part of the message I wanted to get across in this talk was what we're doing now and where we're looking in the future, so that I can get your help, and so that you can just keep an eye on what we're doing and give us guidance where you think we need it. Okay, so this is the current world of the Berkeley Data Analytics Stack. All right, so what's new? I'm going to go quickly here and then get into more of the future stuff, but a lot of you heard about Tachyon. So Tachyon is an in-memory storage system, right, that brings the fault tolerance that you get with Spark to a bigger scope. And the idea is to be able to share data across frameworks and to do so in a reliable way. And Tachyon is now released. It's being used in a number of companies. It's part of a Red Hat distribution. And there's going to be a talk this afternoon by HY, who's the main student behind Tachyon. And so he'll tell you more about it. Okay, but at the storage level, Tachyon and some related things around compression and other types of data access are what we're doing there. I mentioned BlinkDB. BlinkDB is a really interesting project that really gets at the heart of allowing analysts and users to be able to specify where they want to be in the sort of the continuum of getting a perfect answer and maybe waiting a little while for it, versus getting a quick answer that gives them an idea of what they want to do next to make the whole analytics process more interactive. And so the examples we're showing here show that in BlinkDB you're allowed to pose a query and then say, hey, run this query for a certain amount of time and give me the best answer you can give me, and then tell me how good that answer is. So give me error bars on that answer. Or run this query until you get a certain confidence level and then stop. Okay, and we talked about BlinkDB last year at the Spark Summit. What's happened since then is there's been a lot of emphasis on trying to do diagnostics on those error bars. So how do you know that the error bars that the system is giving you are trustworthy? Okay, so that's where things are going on in BlinkDB. And we just had a recent paper last week at the SIGMOD conference, which is the main database research conference on this work. Another thing we introduced at SIGMOD last week is something called the sample clean framework, which is getting at integrating the people aspect with the algorithms and machines parts of the project. And so what sample clean does is it makes the observation that what BlinkDB says, I'm going to look at a smaller sample of the data and then compute on that, and then I'll get an answer faster, but that answer is not going to be as good an answer. It's going to be a fuzzier answer. Sample clean kind of turns that on its head, and it says, you know what? It's too expensive to clean all the data. But if you do that sampling, the sample might be small enough that you can afford to clean that. And if you can clean the sample, you can then take what you've learned by cleaning the sample and then apply that to the answer that you're getting from the system. So you can either just run your query on the clean sample, in which case you'll get an answer the way BlinkDB gives it to you, except it's an answer on clean data. Or you can run your query on the entire data set, but then use what you learned by cleaning the sample to correct the error that was inherent in that larger data set. Okay, and where the people come in here is that in a lot of cases, the way you're going to clean the data is by bringing the crowd into it, right? By having people help you clean the data. And so what I like about the sample clean project is it's an example of sort of this bigger vision we had of bringing together the algorithms and machines and people in a way that let you do something that you really just can't do in any other system or platform. Okay, so that's sample clean, and as I said, that was described last week at SIGMOD. Another project I want to mention is GraphX, and GraphX will be featured in the training session that's going to be happening at this conference on Wednesday. So it's already been released and it's already been used by a number of people. But you know, GraphX is a graph processing system that sits on top of Spark, and what it does is it says, okay, there are certain calculations that you want to do. Sometimes you have data that you want to look at as a graph. Maybe it's a social network, maybe it's a road network, maybe it's a map of some complex computing network. And there are calculations that you want to do on that graph using graph primitives, and that's fine. But as graphs get larger and larger, sometimes it's going to be more efficient and more useful to just look at them as tables. Okay, so what GraphX does is it lets you treat the same data through multiple views. So you can look at data as if it was tables and run SQL and use your SQL tools on that, or you can run graph algorithms on it. This reference to a paper from last year. We also have some work published on our website about GraphX if you're more interested. But the idea is you have this graph, and what you can do is you split it into a table. Then if the graph is big enough, you're going to have to partition that table, and so there's ways of doing that in graph systems. We use this thing called a vertex cut, and that tells you how to take the rows that represent your graph and distribute them across the cluster. Then you can represent the connections between the nodes as a table as well, and then put everything together. Okay, so now we've taken this complex distributed graph, we've split it into tables, and we've distributed it across the cluster. Once you've done that, then you can use relational processing, or things like Spark is good at, to express your graph computations. And what you have to do to make that work is to put in particular systems optimizations to make that go faster. And what this comes down to, in a lot of the cases, is really making certain patterns of joins run faster. Okay, but we know how to do that. And so when you put this all together, you've got an integrated system that takes tables and graphs and puts them together. And what you'll see if you look at the system is we can get performance out of the system that's on par with more specialized systems that don't give you that full functionality and that aren't integrated into an entire stack like BDAS. Okay, so that's GraphX. So this is all stuff that you might have heard about. It's things that the software is already out there and you can use and play with. And as I said, a lot of it's going to be covered on Wednesday in the tutorial sessions. But where are we going next? So what are we doing next? So one thing I want to talk about briefly, so if you remember that picture of the BDAS stack I showed you, we're sort of graduating things out from the bottom and we're moving higher and higher up that stack. And so one thing we're spending a lot of effort on is a system called MLBase, which is meant to make machine learning, in particular distributed machine learning, much, much easier. And so the analogy is, if you think about how you run a SQL query on a cluster, you don't worry about the partitioning, you don't worry about how the data is spread across the cluster, or necessarily even how much data there is. You just write your query. And we want to be able to do the same sort of thing for machine learning. So you say, I want to do this classification, I want to classify this data. The system figures out how to do that in an efficient way that's going to give you a good answer. And so we're building up this entire framework on top of Spark. And the key abstraction that we're dealing with is the idea of a pipeline. And so, a pipeline is really just a combination of operators that are put together in a particular sequence that are meant to run efficiently and give you a high quality answer. And so there's really a compilation process that you have to go through when you take that high level statement of machine learning intent and compile that down into an executable plan that's going to run on the cluster. So this is work in progress. It's, this particular part of the MLBase system isn't available yet, but there's going to be a talk tomorrow afternoon Evan Sparks is going to give to talk in detail about the machine learning optimizer that we're building for MLBase. Okay, so that's one big thing we're working on. Another thing we're working on is really taking a little bit of a 90-degree turn and saying, okay, since the beginning of the lab, we've been focused on large-scale analytics, but what about updates? Okay, so if you look at the big data analytics area, most of the systems are built with this inherent assumption that it's an append-only world. Okay, so log records are coming in, tweets are coming in. Okay, but once data is in the system, we don't really change it anymore. And that's useful, obviously, for a lot of use cases, but it's limiting in a number of ways, too. And in particular, a lot of applications, you need to be able to go in and find a particular record and update a particular record. Okay, and this is something that big data analytics stacks don't let you do right now. And in particular, if you think about implementing real-time machine learning, so even if you're not going to do any sort of transactional updates or updates to specific data items, if you want to provide real-time machine learning, then you probably want to be able to update your models in real time. And that's going to require the ability to do point updates as well. And so we've got a number of projects in the lab that are looking at this different space, right? A little bit away from analytics, more focused on how do you handle updates. And the challenges, of course, are as you spread across the cluster, it gets harder and harder to guarantee consistency and to do that in an efficient way. And so we have a number of projects that involve new programming abstractions. So Planet is a new model for doing transactions across a geo-replicated data set. We have the HAT and highly available transactions and read atomic transactions, which basically relax consistency in some useful ways, and then again allow you to get good performance in a large cluster. And so this is a big area that we're working on now in the lab. And where this is going is if you look at our existing BDAS stacks focused on analytics, right? So we've got Spark, we've got MLlib, we've got BlinkDB and GraphX and so on. What we want to add into that is a component that does serving. So we want to be able to serve data that's being updated on a continuous basis, and we want to be able to serve models that are being updated on a continuous basis. And we want to do that in an integrated way. So if you look at sort of the long-term picture of where the lab is going, this is a good indicator. All right. So those are two projects. Looking a little further and kind of popping up a level, if you think about it, the big breakthrough of the big data ecosystem, it's not scalability, right? Systems have been scaling all along. Okay, maybe the magnitude of scalability is improving, but scalability itself is not that new. And it's not really speed either, although of course we all care about how fast things run. But what's really different, what's really new about the big data ecosystem is flexibility. Okay? And if you compare this to the traditional approach where you have a bunch of data sets, you load them into a data warehouse, there's two things I want to focus on in terms of flexibility. First of all, the traditional analytics stacks, right, based on database systems, had this one way in and one way out. You put your data in the system, you could only get at it through their interface, which is namely an SQL interface. Big data stack split that open. If you want to read the data through SQL, you're more than welcome to do that. But if you want to run MapReduce or Spark directly, you can do that. If you want to look at the bits directly in the file system, you can do that. So no longer is your data locked up behind one interface. So that's one huge step forward. The second one is this idea of having to extract, transform, and load your data. So in the traditional world, you had to define your schema and then make your data conform to that schema before you could do anything with it. In the big data world, that's not what we're doing anymore. You get to load your data first and figure out what it looks like later. Okay, and of course there are trade-offs here, but what this is allowing people to do is just collect data very, very aggressively and then work with it. Okay, as opposed to having to do all the work up front, throw out a lot of your data because it doesn't fit, and then start trying to make sense of it. Okay, and so what's happening here is that ETL is going to be becoming a continuous on-demand process. Okay, it's going to completely change the way these data systems are being built. Okay, so I talked about what BDAS was, I talked about what it is currently, I talked about where it's going, and then some future thoughts. So what I really want to leave you with, though, is just this idea of the importance of research, right? Because at the end of the day, the AMPLab is a research organization. We produce students, we produce research systems. And so what I'd like to say is we have a pretty good track record. You're all here because you love Spark. Spark came from the way we do work. So you might want to think about, well, where's the next Spark going to come from? And I'm going to give you some potential places. It might be the work we're doing on scalable machine learning. It may be the work we're doing on combining serving and analytics. It may be this idea of making data integration and ETL a continuous process. We haven't talked much about single node performance. Clearly, there's a lot to be done there. And if you think about Internet of Things types of applications, pushing processing to the edge, beyond just the cluster is going to be an important thing to be looking at as well. And then, of course, data centers technology is continually changing. You want to be able to track those changes as well. So I don't know which one of these is going to be the next Spark, but I'm hoping that one or more of them will be. Okay, so with that, I'd just like to leave you with an invitation. Visit our website. A lot of the people in the room here are from the AMPLab, either currently or they graduated from the AMPLab. And so, talk to us, get involved, and give us your ideas. Thank you very much.